So what we want to do is we want to introduce some sort of primed reference frame um, to deal with inside the container, okay? So inside the container, we'll call it delta TA prime. For sure, we can say that inside the container that delta TA prime has to be equal to delta TB prime, right? If you're standing inside this thing, you're this guy here. Let's draw a little hat or something so you know who I'm talking about. You will observe this photon to flash back and forth with those same time intervals of TA and TB. Okay. So, well, what's TA? TA is T1 prime minus TO prime. TB is T2 prime minus T1 prime. So rearranging here a little bit, you will get T1 prime equals half of T0 prime plus T2 prime. Now, so there's some things we have to assume here. And Einstein sort of wrote out these assumptions as well in his first paper. The first thing we should note is that T prime in general is going to be some function of that length and the original reference frame time T. Okay, so this is an assumption, and it's a confusing thing. How we're saying that the time inside the container is somehow a function of the length of the container as well as the time outside the container, or if you want to draw it specifically, what the reference point of some person who's standing up. Let's make him orange. Who's standing up here? Okay, and observing all of these phenomena. Okay, and furthermore, he said that it's a linear function. For special relativity, that this is actually a coordinate transformation if you take it really, really far. I'm going to call it alpha L plus beta T. And I'm using my own alpha and beta here, but I'm just showing you that it's a linear function. So what I want to do is I want to write out what are T0, what is T1, and what is T2. Okay, well at T0, if we go back to our diagram for a second, what we can see is that where's the photon? We might say that L is 0. Okay, it's a bit, maybe it's not L, maybe it's some parameter, some length parameter, but what we're saying is this L is a parameter. It's a parameter of this photon and where it's at. Maybe position might be a better variable, but let's stick with L for now. So we're going to say that this is at T, this function, at 0 and then T, okay, which equals beta T. What's T1? T1 is going to be, well, now we're at L for sure. And then we're going to be at some time T plus delta TA. And we already wrote out what delta TA is here. And just to remind ourselves, it's right here, right? So it's this guy. And then we're going to use delta TB after. But this thing is going to equal, it's going to be alpha L plus beta times T plus L over C minus V. Okay, and we can clean this up a little bit, but I'll do that after. And then T2 is going to be again at 0 because you're back at the beginning, and then it's T plus delta TA plus delta TB, which is going to equal beta times T plus L over C minus V plus L over C plus V. Right, once again, that's our definitions for TA and TB that we came up with for that person standing at the origin there, the person who's standing here and observing all this stuff. And with this box flying out here, there's another person in here. So this is the primed and this is the unprimed. Unprimed is this guy. So okay, so now we have this equation we have to put together, and let's do it in pink. We're going to put this one together, and we get T1 is alpha L. I'm going to write beta T, which is this guy here, plus, make sure I'm doing this right, beta T plus beta L over C minus V. equals 1/2 T0, which is just beta t, plus 1/2 T2, which is this guy, which is, once again, we get a beta t, plus, I'm going to sort of explicitly write it out, half beta L over C minus V plus half beta, these guys here, L C plus V. Okay, so what can we do with this? Well, first of all, we're going to realize that this and this and this totally cancel, so they are gone. Secondly, we realize that L, we've got an L here, an L here, an L here, an L here. Of course, they're gone. So let's rewrite this. Let's rewrite this equation. We get alpha plus beta 1 over C minus V equals, let's do it this way. Beta outside of half 1 over C minus V plus half 1 over C plus V. Okay, so then we bringing this guy over, you get alpha equals, let's do beta, and then it becomes negative 1/2 over 1 over C minus V, because we took this guy here, right? We took this guy and subtracted 1 from it, plus half 1 over C plus V. Take the half out, beta over 2, do a little bit of rearranging, and then we switch those guys around. We get this. Okay, we're getting close. So this thing equals, and we'll normalize this fraction. So if I multiply this by C plus V on the bottom, sorry, C minus V on the bottom, C minus V on top, and then we'll do C plus V here, and then C plus V here as well. You're going to get C minus V minus C plus V all over C squared minus V squared. Okay, and then of course C minus C is 0. We get beta over 2, and then we get minus 2V over C squared minus V squared, which equals negative beta V over C squared minus V squared. So cool, we have a definition of alpha that pertains to beta directly. So let's substitute this back in. We knew that T equals alpha L plus, and this variable is questionable. We can talk about that after, what you want to call that. It doesn't really matter. Plus beta T, and we know that alpha equals negative beta V over C squared minus V squared times L plus beta T. And then take the beta outside, and I'll rearrange a little bit. You get T minus V over C squared minus V squared times L. Okay, so I'm going to chop this video off here. This is the first part of this derivation, and it's this formula, and you can see what it's in reference to. T here, we've made it a function of T and L. Really what we want eventually, what we want to aim for, is to get this in terms of X and T. And this is the Lorentz transformation we're going to go for, and everything else falls out from here. All right, guys, so that's it for this one. Please like and subscribe and comment below to tell me what you think.